Hey guys, welcome back to another video, and today we're going to be talking about bubble sort. I'm first going to go over the algorithm and then I'm going to implement it using Python code. In order to explain what's actually going on, let's go step by step. Say we're given this unsorted array 5, 7, 10, 4, 1, and 5. So we're going to first start off by having two pointers. One which starts off at the first element and the other which starts off at the second element. The first pointer is represented in red and the second pointer is represented in green. Each time we're going to check to see whether the number on the red pointer is greater than the number of the green pointer. If the number of the red pointer is greater than the green one, we're going to swap their positions. The purpose of doing this will be clear soon enough. So we currently have 5 and 7. 5 is less than 7, so in this case we're not going to do anything. After comparing the numbers, we're going to move both the pointers by one place. Okay, so now we're going to compare 7 and 10, and again, red is less than green, so nothing is going to happen. And we now have 10 and 4, but in this case, 10 is greater than 4, so we're going to swap the two numbers. We again move each of the pointers by one position. So now we have 10 and 1, and as the red number is greater, we're going to swap their positions again. Finally, we have 10 and 5. Again, red is greater than green, so we're going to swap the numbers, and over here we notice something. The largest number in our array bubbles its way to the ending of our array, hence the name bubble sort. Each iteration we find the largest number. So for example, in the first iteration, we're going to find the largest number. In our second iteration, we're going to find the second largest number, and so on and so forth. So now we have the largest number. Now we're going to repeat the same steps, but now we're going to ignore the last number since it's already in place. Now we found the second largest number, which is 7. So for our next iteration, we're going to ignore the last two numbers. Over here, we need to keep note of a very important factor. When we are comparing the two same numbers, in this case we have two 5s, we will not swap them. And the reason for doing that is because we want to maintain the stability of our sort. This way, the bubble sort remains to be stable. What this means is that it retains the same order as the parent array. And if you want a full and more detailed explanation of what this actually means, I made a short video explaining this concept, which you can find down in the description. Now we have the third largest number. So we're going to ignore the last three numbers. I'm sure by now you understand the pattern, so I'm going to let the rest of the sort run and you can see it complete. And there it is. Our array has finally been sorted after a lot of work. Let's now try to understand the time complexity of using this algorithm. Let's make a table in order to understand this concept. In our table, we're going to see the number of changes made at each step or at each iteration. In the first step, we made 5 iterations, which is the same as taking the length of our unsorted elements and subtracting it by 1. So in this case, it's going to be 6 minus 1, which equals to 5. Similarly, in the second step, we had 4 iterations, and in other words, we have 5 unsorted elements, and we're going to subtract that by 1. 5 minus 1 equals to 4. Then we have 3 with 3, and then 4 and 2, and so on and so forth. And like that, we can find a pattern. Each step has n minus 1 swaps, where n is the number of elements which haven't been sorted yet. And the total number of steps or the total iterations we take are n minus 1, where n is going to be the length of our array. We can now find the total time taken by multiplying by these two, and we get n minus 1 multiplied by n minus 1, which is n squared minus 2n plus 1. We can take an approximation of this and we get an average case and worst case time complexity of big O n squared, with the best case being big O of n. And in the best case, everything is already sorted, so we have to go through our list only once. And as for space complexity, we have constant space, or big O of 1, as all the operations that we performed happened in place. Let's now take a look at how we can write the code for this. Let's look at its pure form per se. In our function, we take in an unsorted list as one of the arguments. We initialize a variable holding the length of our unsorted array. We then go into a for loop which represents each iteration that we make, inside which there is going to be another for loop, and this corresponds to the number of steps in each iteration. So we do length minus 1, as we're going to be comparing our element at the j index with that of j plus 1. And if we do not subtract the 1, at the last element, we're going to go out of bounds and we're going to get an index error. We can check if the element at j is greater than the element at j plus 1. And if that is the case, we're going to swap the two numbers, or else we're going to keep continuing. After we are done making all of our iterations, we return the sorted array. As it is, we get our result, but let's say we have an array which is already sorted. And in that case, even though we would need only one iteration, we would have to go through it as many times as the length of our array. So that's a lot of wasted time. So for this, we can optimize our existing function. For our optimized function, we are going to have a variable flag. So this variable will be set to false, and it will become true only once we make any sort of swap. And we can check for this by changing its value to true only once we enter our if statement. And this is because once we enter the if statement, only then we make a swap. And during each of our iterations, we are going to check if the value has changed to true or not. If it did become true, we're going to keep resetting the value of our flag to false. But if the value of our flag did not change, it means no swaps were made and our array is sorted as it is. And in this case, we're going to break out of our for loop and we're going to return what we have since it's already sorted. Finally, what are the use cases for bubble sort? And the truth is, there aren't many use cases for this algorithm. If anything, it's a great way to first learn about sorting algorithms. The reason they aren't that good is because they have a really slow runtime, with the average case being big O n squared. So this should be it for our video. Hopefully it helped you, and any feedback would be highly appreciated. And thanks a lot for watching, guys, and please like and subscribe if the video helped you. Thank you!